We're on now to, on to chapter 3 from Statistical Rethinking, second edition. So this is a brand new notebook, so the link will be in the description. And before you run, if you're going to run it in Google Colab, you need to come up to Runtime, go to change runtime type. And this is usually set to Python, but we're running this in R. Okay. So chapter 3 discusses sampling as a way of learning about our posterior distribution. Okay. And so I would point you to the lectures either from McLareth or really any number of Bayesian lectures. Ben Lambert on YouTube has many very good ones. And so we're just going to be interested in the practice problems. So the easy problems from this chapter start out with this code, and this code is going to allow us to sample from the posterior distribution of a problem. And so let's walk through this code here. So we are again simulating the globe tossing experiment or data collection from chapter 2. Again, the idea was that we had a globe that was covered in different amounts of water and land. We toss it around. Every time somebody catches it, they have their index finger lands on either water or land, and the number of times that it lands on, I can't remember if it's water or land, but we'll say land. We count that. Actually, you know what? I think it's water because water was more prevalent. Okay. But we use that data to try to estimate how much of the globe is covered in water and how much is covered in land. Okay, and we've used this code in the chapter 2 videos, but just walking through it again. So the first thing that happens is we put out a grid, or with what we're calling P grid here, which is just 1,000 values that are equally spaced from 0, meaning no water, to 1, meaning 100% water. The globe has somewhere between 0 and 100% water. And so this is all of the possible values that it could take on. And then we have a prior distribution, and here we're using a flat prior. And just to show you here what that looks like. Okay, so here's what P grid looks like. Okay, so again, it's just 1,000 values, and you notice that it starts really, really low at 0, gets a little bit bigger, up until we get to 100%. Okay, prior is just 1, and there's a 1 for every value in P grid. Okay, so all it's saying is that our prior belief is that every one of these values from 0 to 1 is equally likely to be the correct amount of water on the globe. Okay. And then we have a likelihood, which is again how we're going to encode our evidence given our assumptions about how the data arose. Okay, and so here we're saying we're using a binomial distribution, d binom. A binomial distribution we would use in cases like this where there's two possible outcomes: water or land, heads or tails, male or female, etc. Okay. And so we are saying that we saw 6 waters out of 9 tosses. Okay. So this code right here will go through, and it will generate how probable that particular data is for every value of P grid, right? So for the P grid value, of, well, let's find probably not going to be any round numbers, but let's say that the P grid number was around 0.5. Well, then likelihood is going to give us a value for having seen 6 waters and 9 tosses if 50% of the globe was covered in water, and again for 51% and for 52, etc. And so we're going to get a value, we're going to get a likelihood for every value in P grid. Okay. The posterior distribution is, it's presented here in the code that's given in the book in 2 steps. One is multiplying the prior times the likelihood, but remember, we need to normalize this by what I have been calling the marginal distribution, but the marginal distribution is just the sum of all of the priors and likelihoods for all possibilities. And so one way to get that is to just put some prior or posterior here. Okay, so now we have our posterior distribution, and again, just to see what this looks like, this is a value. Okay, this is just a value that represents the posterior distribution for every value that was in P grid. That's all that's happening there. Okay. Now, so we can take this information, this bunch of probability, or all these probabilities that are represented in the posterior distribution, and we could do some math on it, and we could answer all sorts of different questions about it. For instance, the questions that we're going to address here in a little bit, but such as, what is the posterior probability, or how much of the posterior probability lies below 20%? In other words, that 20% of the globe is covered in water, 20% or less. Okay, and we could ask all sorts of very complicated questions, and we could do the arithmetic and everything. But at a certain point, that math gets very difficult. It becomes hard conceptually, and some of it is not even tractable. And so instead, what we can do, instead of working with this abstract idea of a probability distribution, we can draw imaginary samples from that distribution. So in other words, on the assumption that our posterior distribution is a good estimate of the thing that we're trying to estimate, we can draw values, or we can pick values within that probability distribution according to how likely those values are according to our posterior distribution. Okay, in much the same way that we created our likelihood here. All right. Now the code for doing this in R is sample. Okay, there's a blurb right here to explain what sample is doing, and we'll walk through it. But if you want more discussion about how this function works with any function in R, you can just simply type question mark and then the function that you're concerned about. Oops. So here I have question mark sample. Let me just put it back in place. Okay, and when I hit this, then you get, well, it pulls up the information about this function that you can read through. Okay. But so we have an object here called samples, and it's going to be filled with our samples, and we create the object that we named samples with the function named sample. I hope that's not confusing. And what is this function doing? So it says, okay, tell me what values you want me to sample from, and that's called x. And so we say x is equal to p grid. And again, p grid is just all of the possible values that represent the amount of water on our globe. Okay, and then how should I sample these? In other words, how probable should each value in p grid be? Well, we want to sample according to the posterior distribution. That's all it's saying. Okay. How many samples do you want? We want, this is 10,000. 1E4 is 10,000. It's just scientific notation in R. And then this last argument here, replace equals true. This just means, so if you imagine these different values in P grid being in a bucket, and I pull one out, and now I want to go pull out another one. And the question is, before I pull out this other one, what do I do with the first sample? Do I put it back in the bucket, or do I discard it? And we are replacing it, okay? And this way, very probable values of P grid, we can draw those multiple times, and that's what we want. So we want to replace equals true. Okay. Let me delete this cell. All right. So all of that to say, here's our probability distribution. We have drawn samples from it. We have 10,000 samples of it, and these represent the posterior distribution. And I'm going to close that. And so now of that posterior distribution, we have 3 questions that I'm just lumping together here. How much of the posterior distribution lies below 20%? So in other words, of our posterior distribution, what is the total probability that 20% or less of the globe, no, yes, that 20% or less of the globe is covered in water. Well, how about above 80%? And then how about what is the posterior distribution that lies between 20 and 80%? Okay. So to answer these, again, because the samples that we've created were pulled from our posterior distribution, they represent our posterior distribution. Let me clarify. They are pulled from the posterior or they are pulled from P-grid according to the posterior distribution. Okay, so finding these values is as simple as looking at all of our samples and counting the number that meet our criteria. So our first criteria is that we want to find all of the samples where P is less than 20%, 20% or less, okay? And so I'm just going to sum, I'm going to add all of the values that are in the object we created called samples that have a value of less than 0.2. And then I'm going to divide that by the length of the samples, right? Because I want a probability. And so that it reads out nicely, I'm multiplying it by 100%. Okay. Similarly, above 80%, well, I want to add all of the samples that have a value above 0.8, and then the same. And then the last one, the posterior probability that lies between 20 and 80%. Okay. And so again, I'm summing samples, and I'm just summing the ones that are greater than 20% but less than 80%. Okay, that "and" there means it has to meet both criteria. Right? And so when I run this through, so this is an actual percent. So for example, 88.8% of the samples are between 20 and 80. Okay. 11.1% are greater than 80, and a very, very small amount are less than 20.